So we will start with A. A is the one where you will get stuck often, and there will be some times in a question you will do a half a page of work only to get to a point like this and then be stuck. So this one is nice in that at least they got you stuck right at the beginning. There are some questions you're going to do on that page where you are going to do a lot of work, and then halfway through your half a page of work on one side, half a page of work on the other side, you will get to this point. It'll look exactly like this, and you will get stuck. This one, both the left side and the right side have no squareds, so you can't use any Pythagorean identities. You might want to try to change 1 minus cos to sine, but it's not true that if 1 minus cos squared is sine squared, then 1 minus cos is not sine. You can't take away the squareds and just say that it works. So this is an example of the build the other side strategy. And one of the ways that you can use the build the other side strategy is say, well, what if I got something the same? For example, why don't I get the denominators the same? What would it look like if I could get the denominators the same on both sides? Now, you're not allowed to move things from one side to the other, but if I wanted a sine theta on the bottom of the denominator on this side, I could do that by multiplying both the top and the bottom by sine. And if I wanted 1 plus cos theta on the bottom of this side, well, I could do that by multiplying by 1 plus cos theta. What that's going to do, and I'm going to leave it factored out, I don't need a bracket there. What that's going to do is at least I'm going to have my denominators the same. And maybe that will lead to something for my numerators. Now, on the right-hand side here, sine times sine, that becomes sine squared. And on the left-hand side, I'm going to have 1 plus cos times 1 minus cos. Now, those are binomials that are conjugates, because the only thing difference is the plus and the minus sign. So you might recognize the top as a difference of squares. If you want, you can FOIL it out, but your outside and inside are going to cancel out. And when you do that, you're going to get 1 minus cos squared theta. Now we've got some squares on the top. You can choose either to work on the right side or the left side. Most people like to change the 1 minus cos squared directly to sine squared. And we are done. How do you recognize ones like this that are sort of build the other side? Okay. In a proof question, you're not allowed to multiply onto both sides. But if you would just look at this one and do a cross multiplication, you would see with the cross multiplication, you would get a sine squared. You'd basically get this on one side and this on the other side. If you recognize that, that can be a hint that you should use some sort of build the other side strategy or multiply by the conjugate to help you solve it. So in your sheet that I gave you, there's going to be ones like that that don't use sine and cos. There's going to be ones that use tan squared and secant squared. There's going to be ones that use cotangent squared and cosecant squared that you can use as a shortcut.
Will there be questions on like tests or exams where you can't prove them?
No. If they say prove, it means that you can prove them on the exam. They're not going out to trick you. Although I have read numerous answers on provincial exams where it's no, it can't be proven. That just means you've made a mistake somewhere. They're not going to trick you and say it can't be proven. In a verify question, it's very possible that they, if they say verify this works, then it will work. But If they asked, does this value make the identity true or not, then you'd have to figure out if they're the same or not.
All the ratios are on our formula sheet, right?
All of, what do you mean by all of the ratios?
Like which ratios are
Well, the identities, the sine squared plus cos squared equals 1 and tan squared plus 1 equals secant squared, those ones are on there. You have to know that secant is 1 over cos. You have to know that cotangent is cos over sine. So those reciprocal ones aren't on there, but the Pythagorean ones are. The next ones that we're going to be learning later today, those super long ones, sine alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. Those ones are on your formula sheet as well. All right. Second proof. Just a quick look at it. I've got cos thetas on one side. I've got cosecant squared thetas on the other. There is no relationship with our identities, our Pythagorean identities, between cos and cosecant. So I would probably start by changing things to sine and cos and getting a single fraction on both sides. Now, on the right-hand side, it's already one thing. It's already one fraction. Even though I haven't changed it to sine yet, it will be one fraction. On the left-hand side, I hope you can see that you have two fractions added together. Okay? So I'm going to start on the right-hand side because that's the easier side. I'm going to do it in 2 steps because you are going to be tempted to do one of the following. You are going to be tempted to either write this as 1 over 2 sine squared theta or 2 over sine squared theta. Take a look at that now and make a decision what you would probably do. Because if you're planning on doing this now and you don't recognize it, you will do it on the exam or do it on the test. So if you're going to make this mistake, I want to see it right now. I want you to see it right now and then learn why you're making the mistake. Okay? The mistake is if you put the 2 on the bottom, that would be wrong. Okay, this means 2 times cosecant squared, and if I do it in 2 steps, that would mean 2 times 1 over sine squared, because cosecant is the reciprocal of sine. Then, if I'm multiplying fractions, okay, I don't multiply top and bottom by 2 because this 2 out in front is 2 over 1. So that would only multiply the tops, and 1 times sine squared would be 2 over sine squared. So if you're also tempted to write 2 over 2 sine squared, I wanted to point that out as well. So to be safe, you could take the extra step and just change the cosecant to 1 over sine squared, and then it follows naturally that you would have to multiply the tops and not multiply both top and bottom, or not move the 2 with the cosecant. Okay, so now we've got our right-hand side as a single fraction. For our left-hand side, right now it's 2 fractions. How do you add fractions? Common denominator. So this one's 1 minus cos, this one's 1 plus cos, and it may feel at the beginning that you are doing a lot of work and making this thing big and ugly. And you might feel like, ooh, I don't know if I should keep going here because now my side is getting even larger than it was before. But maybe it'll work out. Now, the bottom, again, are conjugates of each other. And when you multiply conjugates, you get a difference of squares. So my bottom will become 1 minus cos squared theta. On the top, I'm going to have 1 plus cos theta times 1, and then 1 minus cos theta times 1, and I'm going to add those together. Well, 1 plus 1 will give me 2, and then cos theta plus a negative cos theta, those will cancel out. I'll just have 2 left on the top. Then you see some squared ones. Look for your Pythagorean identities. 1 minus cos squared is sine squared. And we are done. Okay, questions you can do for this one, 12A.